And this is our official start of data mining and share my screen. Here we go. Don't want to forget any steps. And okay. Couple of announcements before we get started on material. First one is that a number of people have submitted pull requests to the repo. I greatly appreciate that. So there's been, I am an imperfect human. I'm not a perfect robot machine. I make typos. And if you see a typo, I mentioned this before, but if you see a typo, you can always fix it and you'll get an extra credit point on your projects section on this class. So everybody who has done that, if you check in Sakai, you will see the extra credit appear for you. Back over here. So onto the PageRank. We're in the topic 101 and computing the PageRank. The notes that are floating around, it's this notes2.pdf file down here. For those of you following along electronically, that's what you'll want to look at. And also the quiz for our PageRank. Recall that every midterm we're going to have a quiz. The quiz is going to be just on definitions, and you must get 100% on the quiz or you fail the class. So the definition is super important, that you really can't understand all of the interesting stuff without just knowing the definitions. And I found in the past that students have tended to ignore the definitions. And so there's a way to force you to not ignore those definitions. If you, for whatever reason, on the day of the quiz, don't get 100%, then you can retake it as many times as you need to. It's just that you'll get a -1% penalty on your final grade for those retakes. The quiz itself, answer key in this quiz-key.pdf file that's in the course repo. And I apologize for the poor quality. Let's see if I can switch to it. Yep. I had to just take pictures of it because the scanner in the department wasn't scanning for me. But all these things are just copied from that Deeper Inside PageRank paper. And so if you've, I don't think there's, I don't know anything too exciting about this, but if you want to ensure that you're going to get 100%, that you have the exact perfect same wording that I do down to the A's and the thes, then you can just memorize what I have here and you will get a good score on the quiz. You will ace the quiz. Any questions so far? No. Question is this contained in the GitHub repo? And the answer is yes. This quiz-key.pdf file, that's the file that you want to look at. And it is right here. You can click on it and download it and get the answers there. Great question. Any other questions so far? Yes. Question is, there was 2 problem definitions, problem 1 and problem 2. The quiz itself is only going to be on problem 2. With the problem 1, those are terms that I thought might be helpful for you to look up, but they're not explicitly defined anywhere in the reading. And so I just want you to make sure that you have some sort of intuitive sense of those terms, but you don't need to know the formal definitions of those terms. So yeah, only on problem 2, not on problem 1. And the actual format of the quiz, like down to the pixel, I'm just going to print out this pages, what is it? Pages, the page number didn't get, but like page 3 and 4, whatever the page is for problem 2 from the notes, that's just what you're going to get on Monday next week. And you'll write out the definitions and hopefully it should be easy. In terms of time for the quiz, there's a couple of options. The standard thing is that you'll have the first 10 minutes of class to complete the quiz. I will be here immediately after the previous class ends. And so if you wanted to get here early to start going, you can do that. Or if you don't feel like, for whatever reason, you don't feel like that will be enough time for you, just come to my office, either in office hours or schedule a time with me. And you can do it with no time limit to take the quiz. Question?
I just got a message from someone who might have been in the
Ah, I see up here people who in the Zoom waiting room. Let's see. Hopefully that admitted people who were in the Zoom waiting room. Welcome, online people. Sorry that I neglected you. Okay, yes, going over the quizzes. And again, if for whatever reason you can't make class, then all the classes are so not only broadcast live on Zoom, but uploaded to YouTube. And if I were having to take the class asynchronously, not be in person for whatever reason, I think my preference would be to watch the YouTube video because I'm not going to be able to really answer questions for people on Zoom or I think the YouTube, most people find it a little bit easier. But however you choose to do it is perfectly fine. Any other questions about what to expect on Monday for the quiz? Okay. Then one last announcement, homework-wise, is your project for PageRank has been posted. It's in this folder right here inside of the 01 computation PageRank folder. If we click it, then we get to the instructions for your project. At a high level, the idea is you're going to create a simple search engine that handles ranking of documents for you. And we're not going to do it over the entire internet. We're just going to do it over a very, very small subset of the internet, just this one blog right here, a kind of interesting one, lawfare.com, lawfareblog.com, where they talk about different national security sort of issues. And you'll be making the search engine for this website. The due date for this is not this coming Sunday, but the following Sunday. So you'll have plenty of time to work on it. From a coding perspective, I think it's super straightforward. My solution to this ends up being less than 10 lines of code. So if you're doing like significantly more than that, you know you're going way down on the wrong path. The 10 lines of code, it's all like mathematical computation, so it can be a huge pain in the butt to debug, but know that it's just not a lot of stuff. So we'll go over, this is divided into 3 sections, this project. One on the background, get you familiar with the data that it's going to be using, and then 2 tasks that you have to implement. So background, what does this data look like? There's a data folder up here, this data folder, and it has 2 files inside of it. These files are CSV files that are gzipped. You don't really need to care about the format of these files because the starter code that I've provided you, which is in this pagerank.py right here, is going to handle all of that for you. But just to get a sense of like how big this data is, this small.csv, this is the sample graph from the inside PageRank paper. So if I can see if I can jump to that, there we go. This paper, sample graph right here. The small is just this very, very small graph. And the purpose of this small is so that you can more easily check that your numerical solutions are getting the right values, because you can sort of just visually actually see what this graph looks like. This file right here, a little bit bigger of a file. If you haven't seen, I don't know, terminal commands a whole lot before, you don't need to necessarily worry too much about what these are doing, other than they're just giving us some insight into the data. The text around these outputs explains what these things are doing. So this command right here just shows us the contents of the file a little bit. And this command right here shows us how many lines are in the file. Each line corresponds to a single edge, or since we're working with web pages, it corresponds to a single link between one page and another web page. So we have about 1.6 million links here in this graph that we're working with. It might sound like a lot, but this is still like what I would consider in the microscopic realm of graphs. In terms of like how the dimensions of our matrix that we're going to be building, how many unique web pages there are, there's about 25,000. So we're going to be building a matrix that's about 25,000 by 25,000. It'll be very, very sparse, so all of your computations will be super fast. So this, yeah, super quick run through there. There's some instructions here on actually running the code. You'll have to do everything from the terminal to access this code. So things like Python 3, PageRank, specify which data file you're using, and then a particular search query that you're wanting to search for. At the moment, all of the results, if you run something like this, they are totally unordered because PageRank is not implemented. So every URL, every page is going to be treated exactly the same. And your first task, actually implement the PageRank method, which will allow you to rank those in the right order. Here's the code. There's, I don't know, 300-ish lines, 250 lines in this file. Lines that you should be looking at right here. This task one, there where you have to make modifications, it's labeled with fix me. It's got and has some small number of hints about what to do. This task one, and again, we're going to talk about like the mathematics behind this all today and at the start of next week. But this task one is specifically implementing this equation 5.1 from the reading. So back over to here, equation 5.1, there we go. This line right here, this bottom line, that's what you have to try to figure out how to implement in the code. And this is, I think, just translating this from this mathematical equation into PyTorch is going to be the hardest part. Again, we're not going to cover the details of the PyTorch library in this class. My expectation is that you'll be able to figure out how to use it. There's not, I don't know, nothing particularly fancy going on with this equation from a programming standpoint, just some matrix multiplications and scalar multiplications, things like that. But in order to make it fast, you will have to use sparse operations. And so this is the inside of the hint right here under task one, it tells you the specific sparse matrix multiplication function that I used in my solution. And so you can look that up in the documentation to figure out how to implement that line of code. The other task, I have after, so all these different parts here have you running it with different options, and it explains, or the purpose of this is to try to get you some sort of intuitive feel for what these different options are going to do, how they're going to affect your results. In class, over the next, again, couple class periods, we'll be talking about the details of the math, proving things about that equation 5.1. I mean, we'll talk a little bit about the intuition about things, but it's really going to be playing around with this, actually experimenting with different parameters that's going to get you the feel for how PageRank works and what it does to different things. So part one is just implementing that one equation, task one, and then another task down here, implementing something called the personalization vector, which hopefully you saw the definition of over the weekend. And there's just this pseudocode right here, which you'll have to implement. And I think actually the pseudocode is longer than my Python implementation. So hopefully, I don't want to say it's going to be easy because there's going to be lots of weird debugging error messages, but it hopefully will not be excessive. For the actual submission for this assignment, you'll create your own GitHub repo. And there's a bunch of these commands that I want you to run, and you'll just paste the output right here inside the README file so that I can look at it and see what did your code do. And then you'll submit the URL of your repo to Sakai. Any questions just about the format of the project, what to expect, how to submit it? Okay. Those of you who have taken previous classes with me, this is a little bit different than the previous assignments that you've had with me because all the previous assignments I've had automated grading scripts that run through things like GitHub Actions to verify that your code is correct. With something like PageRank, it has a lot of floating point calculations, a lot of these mathematical computations. It's really difficult actually to write automatic scripts that check things. And doing that well would be like a super advanced graduate level software engineering course. So we're going to totally ignore the writing good test cases for this kind of code and just sort of look at the output, and you'll have to visually check whether it makes sense or not. And again, due date not this Sunday, but the following Sunday. And we will be using today and next week in class to talk about all the math and the things that are going to go into this assignment. Any questions about anything before we get to the notes, get to the math, get to the fun? Everyone's excited about math? Okay, one yes. Oh, excellent. I'll settle for one. Okay. So today, yeah, we're going over the Pagerank Notes I, and we'll be talking a little bit about some of these definitions as they come up, but I'm not going to be defining them. My hope is that you have looked at these a little bit already, have some sense of what they are, even if they're maybe not like intuitive or why do we care about them. If you feel like, why do we care about any of these things? It's just random words. That's an okay place to be right now. What we're going to do today is we're going to go over these trivial, what I've labeled trivial problems, and that's going to help us get a good sense of all of these definitions and why we care about them, sort of like pushing on these definitions, figuring out what do they actually sort of encapsulate. So we will start with this super easy one, not actually defined in the notes or in the reading, but super important, a stochastic matrix. And a stochastic matrix is just a matrix where all the rows are stochastic. In other words, all the rows sum to 1. So there's lots of examples of stochastic matrices. The identity matrix would be an example of a stochastic matrix. Another example is, let's say we have 0.5, 0.5. That row right there sums to 1, so that's a stochastic matrix. But they don't all have to be the same. Maybe we could have another 0, 1. Or these are all 2 by 2 matrices. It's always good to think about like what's the smallest example, the smallest dimensions of one of these terms that I can think of. So a stochastic matrix, it could be a 1 by 1 matrix, in which case there's only one example of a 1 by 1 stochastic matrix, just the matrix with just a 1 inside of it. Or maybe we'll do a big one, 4 by 4. It's huge. 1, 0, 0, 0, and I'll be lazy on the first one, 0.5, 0.5, 0, 0, 0, 0, 0, 1, something like that. The columns, notice, don't have to sum to 1. In this case, they do happen to. But in this case, we have column of 1.5, column of 0.5. That's totally okay. And over here, they're sort of all over the place. So it's only the rows that matter. Columns don't matter. So yeah, stochastic matrix, examples of non-stochastic matrices. 2 examples of good matrices to keep in the back of your head when you're thinking of examples, trying to see does it satisfy a definition or not, are the matrix of all zeros. That's not stochastic. Everything sums to 0, doesn't sum to 1. Or the matrix of all ones. And I made both of these 3 by 3. That's totally arbitrary. And actually, I made all these matrices square because it turns out for PageRank, we're only going to be using square matrices. So all the things we're going to see are square. But there's no requirement in a stochastic matrix that it be square. So we could have something like this column vector of all ones. It's stochastic. We're not going to need something like that, though. Any questions about the intuition behind the difference between a stochastic and a non-stochastic matrix? Relatively easy. Okay. So irreducible matrix, getting a little bit, how many people before this class had seen the word irreducible matrix? Couple people, not very many. I'll be honest that every time I teach this course, I totally forget. I don't use irreducible matrices outside of the context of Pagerank, so outside of the context of this course. And so I totally forget what it is outside of this course, and I have to relook it up. There's a lot of equivalent definitions of an irreducible matrix, but in the context of this course, what we care about is that if we have some sort of a graph, so like the graph of the web, we'll start with these nodes maybe being URLs, and then we can draw edges between them to represent links. And I'm going to draw all of these as maybe it's might be a little bit clearer if I did something like that, but that's a lot more drawing. So I'm going to draw them all with just double-headed like that. And so I'm going to draw the complete graph as our first little example here, complete graph on these 4 nodes. So complete meaning every node has an edge to every other node. And the corresponding matrix for this graph, if we have, let's use red, I'll label these nodes. We'll call it 1, 2, 3, 4, like that. And then give us row numbers 1, 2, 3, 4, 1, 2, 3, and 4. Inside of this corresponding matrix, we have an entry at the row I, column J, if there is a link from node I to node J. So in this case, we have links everywhere. So I'm just going to put ones in all of the locations. And the idea of the irreducible matrix is that no matter where you start in this graph, you can follow some of these arrows. And if you choose the right arrows to follow, you can reach any other node in this graph. That definition that they provide in the paper is related to how this graph and this matrix relate to each other. There are other definitions that don't talk about graphs at all, that are a little bit more abstract from a linear algebra perspective. But for our purpose, the important thing is the connection between the graph and the matrix over here. So this is an example of a matrix with this graph where you can go from one node to any other node, and it's good. Yeah. Oh, and then the question is, over here, I put ones down the columns, and I just forgot to, I should have, for that particular matrix, also added those as well. It happens to be the case if I did not add those and I had zeros along the columns, that would also be, see if I can get all the ones here correct. I think that's right. This is also an example of an irreducible matrix. That's what I had drawn before. And here you can still go from any node to any other node. So you're okay. Question? Sure.
So you have to be able to travel from one node to any other node within one step. It can't be.
Question is, does it have to be within one step? And the answer is no. You have an unlimited number of steps that you can take to do it. So these examples right here, we have examples where it's going in just a single step. Let's do one more. 2 examples. Keep up the 4 nodes. And here's sort of a minimalist irreducible graph. No matter where you start, you just have to follow the arrows. You go around in circles forever and you'll visit everything. And this will look something like the identity matrix, but sort of shifted over. And so the reason that this is going to become important for us is that there's all these P matrices that the PageRank algorithm talked about, and they're doing different things to them in order to figure out, in order to force them to be irreducible in a certain way, because it turns out that PageRank behaves nicer when the graph has that irreducible property. And so again, anytime you're thinking about examples, trying to get an intuition for one of these definitions, you don't want just positive examples, you want positive and negative ones so that you can compare to each other. And so here in the reducible, so reducible being the opposite of irreducible, the sort of simplest example would be if we just don't have any edges. And again, this corresponds to that zero matrix. Another was one of those good things to be thinking about when you're thinking about these definitions and counter examples. So that corresponds to another important matrix to think about is the identity matrix. And in the identity matrix, what that's going to correspond to is every node links to itself. You can travel to itself, but not travel to anything else. And I'll just say I'm going to be using the identity notation a lot later. So I4 is just going to be, I'll write it out now, but I won't write it out later. And sometimes I'll drop that subscript, just write I. And similarly for this all zeros matrix, I'll sometimes just write that as 0 like that. Any questions about the intuition or definition about reducibility of the matrices? So these are the, at this point, this providing examples. This is a little bit simpler than the things that you'll find on the midterm exam, but sort of towards the end of this packet, we'll be starting to get into questions that you'd find on the midterm exam. And this is just to get us the intuition so that we can do the questions at the end of this packet. So that's reducibility. Next comes primitive. Okay, so primitive, even I think more abstract than irreducible. And so when I'm thinking about examples, I'll just first think about what are the properties that primitive matrix must have. Well, it must be non-negative. Irreducible. And one eigenvalue on its spectral circle. That's the exact wording from the paper. One eigenvalue on its spectral circle. I'll say that the top eigenvalue is unique. I think that's a little bit easier phrasing. Top eigenvalue unique. And so let's start by looking at those examples that we had above and thinking about, do they satisfy some of these same properties? And let's go ahead and switch colors. So the non-negative. All my examples up here of irreducible matrices are, in fact, non-negative. So any of those examples satisfies that. They're all examples of irreducible, so it satisfies that. And so it's just a question of, do all of those have a unique largest eigenvalue or not? How many people here feel like, and this is okay if you don't, but feel like you have a good intuition on whether a matrix has a unique top eigenvalue just from being able to look at it? Okay, 100% okay if you don't have that intuition. I honestly, like, I can't look at a random matrix and also have that intuition, but I can think about certain types of matrices and think about what is their so sometimes when we're talking about all the eigenvalues, we'll talk about the spectrum. The spectrum just means all the eigenvalues. There are certain matrices that I just know what the spectrum is. And so I know whether it has a top eigenvalue or not. Again, simple thing to always think about is what is like the smallest matrix that might possibly satisfy these conditions. And we said before that the 1-by-1 matrix, something like that, it's not negative and it's irreducible. How many eigenvalues does it have? So an n-by-n matrix, n-by-n matrix will always have n eigenvalues. Not necessarily unique eigenvalues, but there will be n of them. And so a 1-by-1 matrix is going to have one eigenvalue, which means that that eigenvalue must be unique. So this is sort of a simple, trivial example of a primitive matrix. Those two conditions from before, this condition right here, based on that discussion of how many eigenvalues does a matrix have. Now let's take a look. Another, again, the sort of matrices that you want to be keeping in the back of your mind as the things to use are like identity, 1 matrix, 0 matrix. So let's look up at our previous examples up here. So identity, 0 matrix, we know we can't use those. Those can't be primitive because they're not reducible. And to be primitive, you must be reducible. So 0 matrix, identity matrix out. This matrix up here, it's the matrix of all ones. And I didn't explicitly write this, but sometimes I'll write that as just the ones matrix or the 1 sub n matrix. How many eigenvalues does, how many, let me ask a slightly different question. Anybody know what the rank of this matrix is right here?
1.
The rank is 1. So we'll write it up here. Let's do it in orange so that it's maybe doesn't get confused with the previous stuff. But the rank of the all ones matrix is always going to be equal to 1. And the rank has a number of different definitions which are useful in different contexts. Again, in a linear algebra class, one of the main things is that you prove the equivalence of all those definitions. Here, the goal is to help give you some more intuition for all those different definitions when you might care about one versus another. And so in this case, what I'm going to start thinking about is that the rank is the number of linearly independent columns or rows. And just by inspection down here, I can see that there's only one sort of meaningful row here. All the other ones are just the exact same row repeated over and over again. So they're not only dependent, linearly dependent, they're exactly equal to each other. And so that's how, just by visually inspecting, I can see that the rank of this is 1. Another equivalent definition of the rank, it's the number of non-zero eigenvectors, number of non-zero eigenvalues. Non-zero eigenvalues. And so if this has a 1 non-zero eigenvalue and everything else is 0, then that 1 non-zero eigenvalue is definitely unique. And in this case, it happens to be positive. So this is an irreducible matrix. And it's sort of the standard simplest example of an irreducible matrix. Right, 1 sub n as my other example. Any questions about, yes?
I'm so sorry. For the reducible matrix, is it that not every node can be reached from another node? Or is it that
So the question is about the reducible matrix and like exactly what is the definition of a reducible matrix. The right way to think about it, the way that I think about it, is that it just literally means not reducible. So not reducible. And if you're going to like actually sort of then plug in what does reducible mean, well, reducible means that no matter which node you're at, you can reach every other node. So irreducible means that there exists some node that you can't reach at least one other node from.
So like if you said add and then you make 5 and then
Yeah, great question. So another way of constructing examples is to take a previous example that you have and add something to it. And so the suggestion is, let's take our irreducible matrix. So we'll do this and red down here. Our irreducible matrix of, so this was our example of the top example of an irreducible matrix, the fully connected graph. Add zeros over here and a 0 over here. That's equivalent. So this is the actual matrix. The graph itself, here's our fully connected graph, plus some additional node that's not connected to anything, makes things irreducible. And so, yeah, one of the things that they talk a lot about in the PDF, the deeper inside PageRank, is that if you're thinking about the matrix that corresponds to all the links in the internet, then there's no way that could possibly be irreducible, because anybody can just add a random link, not linking to anybody else, nobody's coming into it, and that instantly makes it reducible. So yeah, great question. Yes, correct. I drew a reducible matrix down here. Up here, I wrote not reducible. That should be not irreducible. Yes, reducible is not defined as not itself. Lots and lots of nots in that sentence, but thank you for pointing that out. This reducible and irreducible are just opposites of each other, and yeah. Great points. Any other questions so far? Yes.
for the rank, is it the number of linearly independent columns or is the number of linearly independent rows?
Fantastic question. The question is, for the rank, does it matter if we think about linearly independent columns and linear independent rows? And sort of one of the key ideas of the rank is that it doesn't matter. They will always be equal to each other. So whichever one happens to be easier for you to look at, that's the one that you should use. Yes. Question is about linearly independent. What does that mean? And if we have two vectors, so x1 and x2 are, I'll just write Li for linearly independent. If they're running out of space a little bit, but there exists some scalar constant such that x1 equals alpha times x2. So they're only different by a scalar factor. In this case, they're all the same. If we were to have, say, x1 equals 1, 2, x2 equals 2, 4, those are linearly dependent. Sorry, I wrote Li linearly independent. I defined that. Oops, that's linearly dependent. Something is linearly independent if it is not linearly dependent. Again, if so all of these things that we've covered so far today, except the definition of irreducibility and the definition of primitive, these are all going to be in that YouTube video from 3 Blue, 1 Brown about getting the intuition behind the various linear algebra constructs. And again, for this class, that intuition, like the actual properties of the rank or linear independence or eigenvectors, that's what you need to know. You don't need to know how to prove it. You can just take it on faith, and that's fine. Great questions. Any other questions so far? Okay. So primitive matrices, we saw a lot of examples of non-primitive matrices while we were talking about primitive matrices. All of our irreducible matrices above that have multiple top eigenvalues, duplicated top eigenvalues, those were examples. But anything that was not irreducible is also an example. So any of these right here, also examples of non-primitive matrices. So I'll just write identity matrix, not primitive. Somebody shout out why identity matrix is not primitive.
No, not irreducible.
Yeah, so it's not irreducible. It also is all the eigenvalues are 1. So the top eigenvalue is not unique. Lots of reasons why it's not reducible. Something like the matrix of -4, not primitive because it's not non-negative. It has a negative value inside of it. So easy to come up with examples of non-primitive matrices. Okay, and so now why do we care about these 3 key definitions, stochastic, irreducible, primitive? It's because there's these 3 matrices that the Pagerank paper talks about, and we want to know about these 3 properties for each of these matrices. And as they do more things to these matrices, make them a little bit more complicated, we get more and more nice properties about it. We'll be able to say yes and yes to more of these questions. So the first one, we're looking at the matrix P by itself. The matrix P is, again, the matrix that when you have this graph, it's the matrix that directly corresponds to that graph. And we want to know, is it stochastic, irreducible, or primitive? And here, anytime I'm asking one of these questions about does some variable satisfy some property, that's always like, it's not, is there an example of a P? It means that, is it guaranteed? Is the matrix P implied guaranteed for all possible values that are legitimate values of P to satisfy these things? Let's see, what does somebody think for stochastic? Yeah, so it does not have to be stochastic. One example, let's use our 0 matrix, our 0 graph right here, where there's no links between anything. So that's our graph. The P matrix in that case is just going to be the 0 matrix. And the 0 matrix does not, none of the rows sum to 1. They all sum to 0. So it is not stochastic. What about, is this matrix right here irreducible? Why not? I hear mumbling. I don't hear anything I can understand. The nodes aren't connected. So the irreducibility was about you can visit everything. Here we can't visit anything. So not irreducible. What about primitive? Yeah. So primitive requires irreducible. So it can't be primitive. So this is, again, a situation where, and it's okay if you don't have these definitions like down pat perfectly memorized now, but once you get those definitions down perfectly memorized, then say on like an actual midterm exam, if I'm asking you if something's both irreducible and primitive, you automatically know instantly that if you say no here, you don't even have to think, you just say no over here as well. Okay, so then the matrix P bar, how is P bar different than P? The idea of P bar is that we, all of the 0 rows of our P matrix, we replace with a sort of uniform distribution vector. So in this case, this example right here, this P would be 0, P bar would be equal to 0 0.5, 0 0.5, 0 0.5, 0 0.5. Because the only difference between P bar and P is that we replace all 0 rows. Their specific notation that they use is E divided by N, where the E is just a bunch of ones, however many in ones repeated in that you need. And so N is 2 in this case, so we get 0 0.5, 0 0.5. So in this case, P bar up here is, as an example, would be stochastic, but is P bar guaranteed to be stochastic in every possible situation? Yeah, the answer is yes, because that's the purpose of doing this, that we take all the rows that were not stochastic and we make them stochastic. And once we do that, P bar becomes stochastic. Question?
Yeah, when you're saying replace all 0 rows, is it just rows that are all zeros?
Yeah, the question is, when I say replace all 0 rows, that means specifically that the entire row must be 0. So another, if we had, I'll write it right here in a different color. If P was equal to, say, 0, 0, 0, 1, that's a valid P matrix. It just means this node right here is sort of connected to itself. Then P bar would be equal to 0 0.5, 0 0.5, 0, 1. So this 0 right here remains unchanged, stays at 0 because it's already in a row that that has links inside of it. One of the terms that I didn't specifically ask you to find, but that they use a lot in the paper is the dangling nodes. And the nodes that have zeros on their rows are what they're referring to as the dangling nodes. So sometimes you'll see that as a dangling node in the paper. This one here is not dangling. Great question. Yes. Let's see. I see up here, you're saying that the graph I have up here has 4 nodes in it. And so you're right that this P matrix right here is a 4x4 matrix. And since I didn't put the little subscript there, I lost track. So P bar is always going to have the same dimensions as P. So I will go ahead and change that. What that does is it makes all these 0.25s. Everywhere, and then it's yeah. Okay, I'll write the whole thing out fresh. 0.25, 0.25, 0.25. I guess I don't even have room to write it out fresh, but 0.25 everywhere. If I were actually like writing notes for myself, the way that I would write this is that P bar equals the ones matrix divided by 4. So all these entries are the same. They're all equal to 1/4, 0.25. And so the ones matrix, all 4s divided by 4. There's a scalar division right here, makes everything 0.25. Yes, great catch. Thank you. Yes. Okay. Question is, can the matrix, up here we have a P matrix being 0 values, can the P matrix be all ones? And the answer is no, it can't, because part of the requirements of the P matrix is that it be stochastic. Sorry, every row that is non-zero is stochastic. So all ones divided by far, this would be a valid P matrix right here, where every element is equal to 0.25, but the sum of every row must be either 0 or 1. Okay, so the P bar matrix, we said, okay, doing this one change right here, replacing all the 0 rows with the E divided by N, that gets us the stochasticity property. Does that get us irreducibility?
No,
Why not?
because we can still get stuck places.
Do you have an example?
Sorry, yeah. Do I have an example off the top of my head?
So we have 3 good example matrices to always think about: the 0, the 1, and the identity matrix. Let's think about the identity matrix. Good choice. So if we have the identity matrix, we'll stay with I4 like that. 1, 0, 0, 0, 0, 1, 0, 0. So that's our identity matrix. We'll say that's what P is equal to. There are no non-zero rows, so that is also what P bar is equal to. And if we think about the graph for this, if we were to plot out the graph, we'd have these 4 nodes right here, and they would all have edges to themselves like this. But there's no edges anywhere else. And so no matter where you are, you're going to be stuck. And so it is in fact reducible. So not irreducible. And we know from just instantaneously, that means that it cannot be primitive as well. Yes. This is an entirely separate example, yeah. Great questions. Any other questions about this problem here?
I have a question about the pi. What's the proper definition for that?
So are you referring to the PageRank vector or the pi vector?
Yeah.
Yeah, saying either pi or PageRank vector is fine.
Vector. So that's like the steady state equilibrium for the stationary equilibrium for the matrix.
Yes.
If that has a 0 entry, is that sufficient to say that the matrix is reducible?
So the question is here, how does the pi vector relate to the to reducibility? And the answer is that for our purposes, pi is only defined when the matrix is irreducible, when you can get everywhere. If you can't get everywhere, then pi will depend on this personalization vector thing. It's always going to be the case that pi will be, so this is not the definitions, but I'll just write out some properties of pi related to the question. Always the case that pi has all strictly positive, so non-zero, greater than 0, strictly positive entries. And as we'll see next, it's going to be because this PageRank vector is defined in terms not of P or P bar, but in terms of P bar bar, which is guaranteed to always be irreducible, guaranteed that you can always go anywhere in the graph. Yeah, weird things happen if you were not to have that P bar bar, which would cause some of these to be 0, and weird things would happen. Great question, great thing to be thinking about, but not something that you have to worry about in the context of our class. So P bar bar, Is it going to be stochastic? Well, first of all, let's remind ourselves what is the definition of p bar bar. So p bar bar, again, this is something that you're going to want to have just like instantly, that you can instantly recall, because first of all, you're going to need it for the quiz, but also to be able to answer questions like this, you need to know the definition of it in order to be able to think about what properties does it have. So it's alpha p bar plus 1 minus alpha e v transpose over n is the definition they give for p bar bar. They actually have two different definitions, one where it's EV transpose and one where V is just equal to E, so it's E transpose over N. And either one of those is fine for our purposes right here. So this right here is going to be stochastic. The answer is yes, it will be. Turns out that this thing on the right is stochastic, this thing on the left is stochastic, and averaging them this way is going to guarantee the stochasticity. So yeah, proving that's a bunch of algebra manipulation that we don't have to worry about. In the paper, they just actually state p bar bar is stochastic. So if you, yeah, so that's good enough for us. Yes, stochastic. What about irreducible? Yeah, it is going to be irreducible, and that's based on this extra additional term over here. This EE transpose, that's equal to what I've been calling the one matrix. It's just ones everywhere. And so they're dividing it by n so that it becomes a stochastic matrix. And so when we somehow mix in ones everywhere into the graph, then every entry is going to be non-zero. And so there'll always be some probability of going from one entry to another entry. So it's going to be irreducible. For primitivity, the thing that we have to check, there's the three conditions. Is it non-negative? All of these p bar non-negative, this thing over here non-negative, so it is non-negative. Is it irreducible? We've just checked that. The next thing is, does it have a unique top eigenvalue? And the answer is yes. It turns out that the proof for that's actually contained in the text at some point. I think it's theorem 5.1 shows us that it is in fact primitive, because theorem 5.1 actually tells us what all of the eigenvalues of the matrix are. And yeah, let's go ahead and take a look at that. We have time. There we go. Theorem 5.1 states that these are the eigenvalues right here. The top eigenvalue is 1, and all the bottom eigenvalues are alpha times something where alpha is less than 1. So the top eigenvalue is unique. And if you like math, you like linear algebra, feel free to read the proof. But in this class, you're not going to need to know the proof. You'll just need to, some of the problems will be greatly aided by knowing the statement of theorem 5.1 here. Where'd we go? There we go. So yes, so the p bar bar, the reason we did all these things to the original P matrix was to get that stochasticity and primitivity to our matrix. Any questions about any of that? Yes. Question is, where does alpha come from? And the answer is that alpha is what we call a hyperparameter. So it's a parameter that's selected by users. And one of the things that they state in the paper is that Google famously used 0.85 for their alpha because Larry Brand and Sergey, whatever his name was, thought that that was a cool number. Yeah. Did I get their names backwards too? Larry Page, Sergey Brand. There we go. They had no idea. They were just trying stuff that seemed to work well. One of the things that you're going to have to do in your programming assignment is You'll be experimenting with different values of alpha. You'll see how that affects like runtime trade-offs versus versus the quality of the search results. And in the next notes packet, which I don't think we're going to get to today, we'll be exploring how some of the mathematics behind why it turns out 0.85 is a good choice. We can sort of somehow prove that, but they were just doing trial and error. Great questions. Any other questions so far? Yeah. Yeah, so the question is, let's do an example. Let's see what would something of p bar bar actually look like. And so in order to do that, I'm just gonna come up here to some blank spots. And so if we have P being, so we'll start off as just, so there's two nodes, and maybe we'll just make it a little bit more interesting, make that one as 1 and that one as 0. So we have an edge between nodes like that. P bar, set the zeros to 0.5, 0.5, 0.5, 1, 0. And then P bar bar equals alpha times P bar plus 1 minus alpha times E transpose over N, in this case 2. So for simplicity, we'll set alpha equals 0.5. So it's just a straight average between the thing on the left and the thing on the right. So we'll calculate what the thing on the right is. This thing on the right, that right there, is equal to, so E transpose is the matrix of all ones divided by 2, 0.5, 0.5, 0.5, 0.5. And now the average between that and that top row stays the same. Then the bottom row, 1 average 0.5, 0.75, 0.25. In general, what you're going to find is that the P bar bar is not going to have any zeros in it. It's going to have a bunch of things that are just been sort of smoothed over a little bit. The really big numbers in the P bar matrix will get chopped down a little bit. The really small ones will get brought up a little bit. And the really medium ones will stay really medium. Okay, I want to make sure. So let's see. Yeah, we're going to push ahead here into this section about prove or give a counterexample to all these following claims. This is to help continue giving you some more practice with linear algebra, review concepts, but also to make sure that you're understanding like the construction of all of these P vectors or P matrices and their implications. And so we're not going to have time to finish all of these things here. But these are the sorts of like level of difficulty that you should expect the midterm questions related to this packet to kind of be. That'll have some random linear algebra term and ask you, is one of these interesting matrices that we like, does it, yeah, what are the properties of that matrix? We're exploring the properties of these matrices based on their construction. So here we have the rank is the P bar bar is equal to 1. The vast majority of these are going to be counterexamples. They're going to be false statements. So that's a hint. The things that are true statements, it's just going to be like a one-line thing of, yeah, super straightforward explanation. It's like by definition, or that'll be by theorem 5.1 from the paper. If you're finding yourself like doing lots of complicated calculations, you're going down the wrong path. All of the examples that you'll want to use, again, should be thinking of the like web graphs that are either fully disconnected or fully connected. 3 is easier to draw than 4, or things that are like the identity. Those are the 3 good examples that you want to consider. And Pretty sure all my counterexamples come from one of those three examples. So in this case, we just want to know, like, what is the rank of the p-bar bar? We want to know how many linearly independent rows does it have? And we're trying to find a counterexample of p-bar bar having only one as its rank, only one linearly independent row. If I'm trying to find something with not one linearly independent row, but many linearly independent rows, I want something with a high rank. Which one of these things should I start with? Which one of these is gonna has a high rank when I write it out as a graph? So again, as a matrix, this is the 0 matrix, this is the 1 matrix, this is the identity matrix. Which one of those has the highest rank? The identity rank of the identity equals to n. So that's trying to find my counterexample. Want to find something that is probably going to make p-bar bar not have a small rank. It's going to have a large rank. We know p-bar bar is related to p. We always start our constructions with p. That's sort of the most basic thing. So let's just try that p equals the identity and some arbitrary number of nodes. And this has no 0 rows, so we can say that there's nothing to do to construct p-bar bar. P-bar bar, sorry, just p individual bar like that, will be equal to p, which is also equal to in, yep. And then the question p bar bar here equals alpha times p bar plus 1 minus alpha E transpose divided by n. And plugging in some of the things that we know, this is equal to alpha times I sub n plus 1 minus alpha times, I'll just go ahead and replace the EE with the 1. The 1 divided by n, like that. And so we have a high rank thing over here. The rank is n. We have a low rank thing over here. What is the rank of this thing? The rank is 1. The rank of the all ones matrix is going to be 1. And we know that when you have the sum of two matrices like this, sum of the two matrices, the rank of the sum can at most differ by the rank of this rightmost thing. So this rank of p bar bar must be greater than or equal to n minus 1. The most that adding a rank 1 matrix can do to modify the rank is change it by 1. So the rank is at least that. As long as n is greater than 2, then we have a counterexample to this up here. So something like this right here would be my counterexample. I'll circle it just so that we know that's the counterexample. These ones over here are not counterexamples. Any questions about why that's a counterexample? A lot of questions? Okay.
So, how do you create alpha IA plus 1 minus
Yes, the question is how I went from this last green step to this step up here. And let's see if I can write it out a little bit more formally. So let's imagine this is two matrices, A plus B. It's just a fact that the rank of A plus B must be greater than or equal to the rank of A minus the rank of B. Assuming A is the larger of the ranks. That's just a property of ranks. Yeah.
So like when you're actually trying to find
yeah, so when you're doing these counterexamples, if there's a particular alpha that is helpful to you, you can pick whatever you want. In like the real world programming problems, we'll see, and starting in the notes next week, we'll see that there's going to be actual like trade-offs that if you make alpha really large, you're going to have to do a lot more computation. Your program's going to slow down a lot. And if you make alpha really, really large, then in some contexts that gives you better results, but some contexts lower alpha actually gives you better results. So yeah, it's a and in terms of the counter examples here, I can't think of any situation where a particular alpha is going to be like helpful or meaningful in any way. And because Google uses the 0.85 as an alpha, if you just have to like think of something concrete, then that's what you should be thinking of in your head. It's something that's kind of close to 1, but it's not yet at 1. See, I can't quite tell the time on the clock from this angle. I think it's pretty much the end of class at this point. So we'll stop here. We're not going to go over any of these other examples, but those are things that you should be able to know for the midterm exam. And again, on the midterm, you'll have access to your notes. And so potentially one of the problems could just be like exactly literally one of these problems, and you just have to copy it over to the midterm. Or they could be slightly different. I'll stick around as long as anybody has questions. Oh, I also forgot to mention I posted an issue about office hours, Tuesdays and Fridays. I tried to make them at times that I thought would be not conflicting with a lot of classes. But I'll always be available for questions after class, or next time would be Friday at 11 office hours. Hope you all have a great weekend.